Alright, so today we'll be talking about long tail distributions. So these are naturally occurring distributions, and as it is very intuitive that we have some head classes which have a lot of examples, and we have a lot of classes coming under the tail category which are having quite less samples, and this is very much visible in vision related data sets, because we as humans will always tend to have more images of some of the popular classes. Like we'll always have tons and tons of images for be it cats and dogs, but we'll always have less images for, let's say, whales, seahorses, or other rarer things that we interact with. So this is something that is naturally occurring, and this is an issue for machine learning models at large, because generally we try to minimize our error rate, and this can be easily flawed. Like if the model only focuses on the head classes and ignores everything from the tail class, like it has very poor generalization for the tail classes, it will have a very bad generalization for the real world case, but it will do fairly well on the training set. So this is an issue that we try to mitigate, and this can be really important because some of like in image recognition tasks, some of the classes with very less examples, which are rarer, tend to have more information. Like it would be more exciting to let's say spot a cheetah in a grassland as compared to grains of wheat or like any other plants that are very common in a grassland setting. And there are various measures of imbalance which can be used to quantify how imbalanced the data set is. One is simply by taking the class with the maximum frequency and dividing it with the class having the minimum frequency, which is the first one. Second one is comparing the standard deviation, like we chart out the entire frequency versus class chart and see how the standard deviation goes. But this is a comparative one. And another would be to compare the mean of the frequency and the median of the frequency, like basically how many examples do we have for each of the class. And another one, which is coming from economics, is the Gini coefficient, which is a measure of inequality, and it ranges between 0 and 1, 1 being the most unequal case, as in all the samples are coming from a single class, and 0 being the equal case, that all the samples have the same amount of examples. And some naive methods that can be used to try to treat these imbalances are like undersampling the head classes, but this could result in really poor performance, because then we'll have the same number of examples for head classes and the tail classes, which will also make our generalization poor on the head classes as well. So this is not something that is recommended. Another one could be oversampling the tail classes, but this has the issue of like we try to, if we only have limited data for the tail classes, and that too has some noise or has some error, like it would be a systematic error, then we'll have effects of the error compounded. Another one would be to interpolate data points. Like let's say for a weaker class, we have one data point being here and another one being here. We'll try to randomly take a point just between these 2 points and assign it to the minority class, and this way we can create some data points. But this is fairly simple, and this is how SMOT really works. But this has the issue, like we'll have to do this for multiple classes and multiple times to generate samples. So here we are trying to use contrastive pairs for learning. Contrastive pairs are very simple to understand. Like you will have positive samples. This is with respect to a reference class. Like let's say if my reference class is currently a dog, positive samples will be images of the dog, of like other dogs, or like of the same dog from a different angle. Basically they'll have from the same class. And negative samples will be like examples or samples from another class. This could be like an image of a cat or so. And logic adjustment is simply taking in a factor of the frequency of the class in our final softmax. Like softmax is generally used as the last layer in a neural network, where we probabilistic idea of how well a particular class is, as in if I have how higher of a chance I have for a particular class. So we for that we simply take the output of the neuron and take an exponential divided by the sum of all the exponentials we have, like from all the neurons, which is the basic softmax formula. And here we'll take into account, like, let's say the frequency of the class fi. Lambda is just a scaling parameter. So higher the frequency of a class, higher will be the penalty of sorts, and the effective zi will be reduced. So as you can see, then the e to the power of zi will be reduced as well. So for a class with a higher frequency, the exponential would be a bit less, and this would allow our model to focus more on the rarer classes. This is just a finer adjustment. In this paper, what the authors propose is they have a very strong assumption that all the features of the data set, like for all the images, all the features lie on a VMF distribution. VMF is von Mises Fisher, which is generally we have a Gaussian on a 2D surface, right? But intuitively, if we spread it out over a sphere or a unit hypersphere, and we try to have a Gaussian of sorts on that. Like this can be easily defined by a mean of like where the concentration revolves around, and a concentration of the samples. Like this is very simple to understand. Yeah, you can see here it's K is actually the concentration parameter. K is 0, so it's a uniform sphere. And as we move higher up the concentration, we'll have data points collected near a particular point where the mean is. So it's given by this function, the probability density function is given by this. You can see it's an exponential of the power of the concentration and the mean, and C of P is just a function that has a Bessel function involved in it, and we'll have a smaller trick to calculate this Bessel function easily, because we do not have higher order Bessel functions in PyTorch, because it's computationally very costly. So I hope you have understood what VMF really is, and this is a very strong assumption that the authors have taken, that all the features are on a unit hypersphere following a VMF distribution, and this is where the entire paper revolves around. So PROCO is actually probabilistic contrastive learning. They have just abbreviated it to PROCO. So we estimate the feature distribution of the VMF, like we only have to estimate the mean and the concentration. And once we have estimated how the hypersphere looks like, we can easily generate pairs of the data. Like for let's say our reference class is once again a dog, it will be very easy to generate other samples using the distribution for dog itself. And for other samples, like for samples not belonging to that category, it's simply fairly easy to generate negative samples as well. And our earlier case, which is supervised contrastive learning, is limited by the actual samples in a batch, because we cannot generate any more samples. And this also has an issue, like I'll refer to the doc once we are done with this short presentation. And our goal here is to maximize, in both the cases, it's to maximize the similarity between the anchor class and the positive class samples, because they're of the same class, right? And we'll have to maximize dissimilarity between the anchor class and the negative class. Basically, we'll have to separate them so they have a much clearer boundary as well. And I don't know why this is glitching a lot. But we have a loss function of sorts here, and this has a lot of heavy notation. And as you can see, we have a tau parameter here, which is also called a temperature parameter, and this is just a scaling parameter. As if we enlarge this tau, the softmax will become sharper and our results will be towards a certain class. And if we have a very large tau, we'll have a smoother softmax, and we'll have let's say more number of classes, which can be the probable solution. So this for this we just have like the numerator pushes for the anchor class and the positive class to be together, and the denominator tries to have the anchor class and the negative class as far as possible. So this is just the positive and the negative term which have been separated out for Proco, which I'll be explaining much better in the document that I have. And the final thing that they have incorporated is a two branch architecture. Like basically, they have a classification branch and a representation branch. So they use both of these adjustments that I've suggested. Like they'll use logit adjustment for a single branch, and they'll use Proco for another branch. And these will have a shared branch or a backbone for like basic pre-processing and stuff, like to put it and in an easier way, simply understand it as a tree of sorts. Like you will have a simple node here which will feed in the data to these two children nodes, and based on results of these nodes we'll get an answer. So the final loss function is just addition of these two. Like we have something from the logit adjusted part and something from the Proco. Alpha is just a scaling parameter here. So moving on to this, like I have also written a Medium blog on this, which should have some images as well from the presentation, but this is quick and easy to understand. So here we are. So actually this is a paper from Tsinghua University. I hope I'm pronouncing it right. It was really fun to go over because it was small and it was really interesting. I also read a literature review paper on this. So as we covered, key long tail distributions have like learning of tail classes severely underdeveloped, and data is often insufficient for the tail classes to be learned, and this is what we have. We discussed this measuring long tailness of a distribution, and naive methods we also discussed. Data augmentations mode, we talked about this. This is really intuitive. Like oversampling, we try to create more samples of the minority class. Undersampling is like reducing samples of the head class. Data augmentation is creating some sort of data pairs. Contrastive pairs, I hope you have understood using the dog and cat example. It's very simple. Here it's also the same example. Like if anchor is a cat and the cat becomes a positive example and a dog becomes a negative example. Logit adjustment is just having a frequency parameter incorporated in the softmax. VMF is a Gaussian, assume it's similar to a Gaussian but on a hypersphere, has concentration and mean as its parameters, right? We have a Bessel function which is denoted by IP. It's in the probability density function of our VMF. This is the diagram we already saw. Then what we are essentially trying to do, we are trying to estimate like the mean and the concentration of each of the features, and pi is the frequency of the class. This table we have already seen. And this is what I was talking about earlier. Like when we divide our training loop into batches for like maybe spreading it out across worker nodes or something similar, we have to divide it in some sort of batches. And batch size is really important for the tail classes as well, because if our batch size is too small, like we are only processing 200 images once, it might not have a lot of samples from the tail classes. And for the tail classes, it will not have a lot of positive samples, but it will have a substantial number of negative classes, right? And this can be the case for like a very highly skewed distribution. If only like let's say one class has a lot of samples and all the other belong to the tail part. So this particular class will not even have a lot of negative samples. So that's an issue. And if we have a larger batch, this will obviously bring in computational requirements, which is listed here. And so we try to avoid this thing altogether by learning the VMF distribution and trying to generate pairs from the distribution itself. So uh, this is already seen earlier. This maximizes the similarity between anchor class and the positive samples. The denominator is for the anchor class and the negative samples. We try to keep them as far as possible because the VMF is a learnable space, right? We talked about the temperature magnitude, scaling magnitude, and we talked about the goal of a loss function as well. So as we saw, like mu is the directional mean for class yi, and this is just the contribution of class concentration, which is k, to positive similarity, what we had in the numerator earlier. And this is a subtle modification of the previous one. Previous one was for supervised learning, and this is for proco, which is a slight modification. Like k tilde is just like we factor in the frequency of the class, which is pi j here, and tau is once again the temperature parameter, and this is the norm, L2 norm. And C should be the one having the Bessel function, right? Which we saw earlier. Let me scroll. C is this one, like this term. So it has the Bessel function right here. So you see, as we move P up, we'll also have to calculate higher order Bessel functions. And for that, you make use of a recurrence relation, which is right here, because it was in the paper as well that we don't have calculations for higher order Bessel functions in PyTorch. So that was a neat trick they incorporated. Like it's a very simple, like we scale our current sample and we just take a difference from the previous ones, and that's our current Bessel function. And we've reached towards the end. We have a two branch design. We feed both of the branches with a common backbone, and one uses the linear classifier, one uses a neural network with Proco. So this is how we try to learn the feature representation in a VMF distribution, and based on that we generate pairs, and after that we arrive at a final loss function which we try to reduce, and based on that we can have a good generation for the tail classes as well. So this was a very simple explanation of this paper, and this was really fun to read once again. And I even sent out a mail to the authors, which for PhD grads. So this was really fun. I wish I had some more images to end this too. And if I'll definitely link all these in the description as well. This will be fun.